Morning, everyone. Can you hear me okay? Okay, good. So thanks for the invitation. There we go. Much better, much better. Thanks for the invitation. It's an honor to be here. I've got many collaborators in Japan and always look forward to the visit. This time I made a little time to go to Kyoto before I came down for the seminar. And although it rained, it was pretty stunning. So what I'd like to talk to you about is extreme heterogeneity. We organized a workshop last year in the Department of Energy on this topic, but it's been a popular topic for my group for some time. And so what I want to do is take a few minutes and just talk about the trends in high-performance computing and computer architectures at large. As you know, power has been a major constraint, and it's really driving architectures and dimensions that we haven't seen before. And this is not only the processor design, which often gets much of the focus, but memory systems, I/O systems, and other components are being transformed as well. I would argue that power isn't our main challenge right now. I would argue it's complexity. I think systems are getting so complex that, number one, they're becoming very difficult to design properly in terms of correctness and getting the performance you expect out of them. And then number two, programming these systems is becoming increasingly difficult, and I will show you some evidence of that in a moment. I would argue we're reaching a state of crisis on this front because codes just have to be rewritten for every new architecture that comes along. So what I'm going to focus on is heterogeneous processing and basically the programming systems. I'll give you a couple of examples of what our group is doing. The first one is using OpenACC to map applications to FPGAs. Now, if you've worked with FPGAs before, you know they are sometimes a very complex beast at program. We have some promising results there where we can take the same application using OpenACC and map it to a GPU and map it to an FPGA. And the user doesn't know much about that mechanism underneath the hood, just mapping that. The second one is something we've just developed over the past year called Iris, and it's an intelligent runtime system. Now, obviously, what do you mean by intelligent? What I mean by that is that you can write your application once and run it on many different platforms without any user intervention. And it can be in the same node, and I have some examples I'll show you in a moment where we have one application running in a node with FPGA, GPU, and CPUs, and this runtime system is mapping the tasking to those. There's some other areas that I will not have time to talk about that I wanted to briefly mention. The first one is CLAC. We're actively developing OpenACC support in LLVM, and we hope that will be upstreamed in the next couple of years. This next one is we're developing an OpenACC dialect for MLIR, which is a new intermediate representation that is being advocated by Google. And we hope to use that with the new Flying Fortran compiler that's being developed in ECP. Then there's a bunch of other fun topics in emerging memory hierarchies, especially non-volatile memory. We think that's transformative for these systems. So before I go too far, I have so many experts in the room, I want to take a quick poll, okay? So think 10 years back. How many of you would have predicted that many of our top HPC systems would be GPU architectures today? So just, be honest, raise your hand if you think many of the top systems would be GPU systems. Good, good. So that's about what I would expect, probably 10 or 15%. So now, think forward 10 years. How many of you predict that most of our top HPC systems will have the following architectural features? Okay, assume that we're just going to have a multi-core of some kind in the system. How many of you think it'll have a GPU next to the CPU? How about an FPGA or some type of reconfigurable processor? How about neuromorphic? Ooh, I just see one hand. Two, okay. How about a deep learning processor that does inference and training? Okay, that's about the most popular one so far. Okay, here's everybody's favorite this year, quantum. How many of you think you'll have a quantum processor? I see a broken hand there. Yeah, so I'll say a little bit more about that too. How about RISC-V? How many of you know what RISC-V is? How many of you think we'll have a RISC-V supercomputer in the next 10 years? So, okay, just, about 5 people it looks like. And then, of course, there's always new unknown processors that are kind of unfair to ask. The last option is the one that we see emerging now. It's really all or some of these features in one SoC, right? And that buys into this idea of architectural specialization. Now, what are the implications of that? And we're seeing this in DOE and ECP, and I'm sure you are too, based on some of the talks we saw yesterday. Imagine you're building a new application with 3 million lines of code expected, and you've got 20 team members, and you're going to work on this over the next 10 years. What on-node programming system do you tell everybody to use and invest all that time and effort in? So here's at least a subset of the programming models and things that are available today. Okay, we can assume we'll have C and C++, and probably Fortran. Hopefully Flang will help make that live forever. But then you have metaprogramming models like Cocos and Raja, Sickle. You have CUDA, HIP, OpenCL that are a bit lower level. Then you have directive-based that are good when they work. They have to map the data parallel loops into the accelerators. Then you have the scripting that's taken over in machine learning. And then, of course, you have things like domain-specific languages and frameworks. And then, think about it. TensorFlow really didn't exist 5 years ago, right? At least in the public forum. And so it just really came out of nowhere. And now a lot of people are doing TensorFlow. So there's always the chance that could happen. And then again, you could have all of these glued together. And that's, again, kind of what we're working with today. We see applications that use many of these. So with that, let me dive into the meat of the talk. So the vision I want to portray for you today is in this very high level layering of the different topics. So the first one is applications. So I'm going to tell you a little bit about applications in ECP, but I'm also going to tell you about a new application area, streaming application area we're working in that is encountering the same problems. So it's really not just HPC. The second thing is the programming systems. Now, I've told you a lot about that up to this point, and I'll tell you a little bit more about what we're doing in directive-based compilation to try and solve this problem. And then the runtime systems are becoming more and more important. It's becoming increasingly important to be able to discover new resources in the node, schedule, manage data movement, and even do that load balancing without any user intervention so that you can run across many different platforms. And then architecture is obviously at the bottom. That's where a lot of the action is happening, for better or for worse. So applications. So I just want to put a couple slides in here to set the context. So ECP and Mike Rowe will be on and be giving a talk later today about ECP and ST. I wanted to put this slide in just to give you an idea of the breadth of applications that are going on in the Exascale computing project. Right now, it's about 24 applications teams that have significant funding, and they're all trying to prepare for Frontier and Aurora, the two systems that will be deployed at Oak Ridge and Argonne. And so they're asking the exact same questions I was asking you a few minutes ago. You see AMD with HIP, you see Intel with Sickle and OpenMP, and so we get a lot of questions about the path forward there. But it represents quite a wide variety of applications, many of which I think share common traits with some of the presentations we heard yesterday. A more interesting application area that we started working on recently for DARPA is one of software-defined radio. Now, just in a 1-minute description, software-defined radio is really a You can buy hardware these days called USRPs that are transmitters and receivers, and they're completely software programmable. You can buy these and plug them into your USB port and start listening to RF signals or transmitting RF signals. And those are just programmable. So whatever you decide to program them with, you can access those signals. What we're looking at here is the GNU radio and a mock-up of it running on 2 Xavier NVIDIA SoCs. And it's just sending Wi-Fi signals. And it's not using the Wi-Fi that's built in. We're trying to make it work on this platform, just using some of the programming techniques that we've been developing. The point here is that, again, it's not just HPC that's hitting this challenge. The software stacks for these embedded SoCs is even more complicated than what we're dealing with. So that's a really quick view of the applications that we're focusing on. So let's talk about the driving trends in architectures. So many of you know that we're approaching fundamental limits with contemporary devices, and so there's plenty of references and talks you can see about that. A lot of people have predicted the end of Moore's Law, right? And here's a chart that shows some of those predictions. A lot of people have been wrong. I particularly like the one that goes out to the year 2600. I guess they only will be wrong once, because when Moore's Law actually ends, they'll just miss it by that one. But the things we're seeing in business are real. And so if you look at the investments it takes to start getting down to the level that we're talking about with next generation processes, it's becoming a very small game in terms of the number of competitors. And if you look here at this chart, I grabbed from Wikipedia, you see how the number of foundries has just dwindled. And right now, TSMC is talking about 5 nanometer being ready. But, I don't know about you, but one vendor is probably not enough. I know some people are depending on them now for shipments, and things like a pandemic can just put a hiccup in your entire timeline, right? And so that makes it really good to have more options than that. So not to be bleak, but let's be more optimistic. So I like to think of this in terms of the 6th wave of computing. This great chart I got from Ray Kurzweil, the futurist, on his online website, and it really shows how computing has increased over the years in terms of performance per cost. And so you see the transistors, integrated circuits is really what we've been benefiting from all these years. And it's really amazing. If you go read some background material on this and see how much it's improved, it is unlike anything we've ever seen before. Well, let's think about it scientifically. I think we're just entering the 6th wave, right? So I think that's where we are, and several things are happening now that we need to prepare for. So these are really the 3 things. I think optimizing software and exposing new parallelism is something our community is outstanding at. We do it a lot better than many of the other organizations out there. If you look at emerging technologies, which I mentioned earlier, you have things like quantum computing and neuromorphic and carbon nanotube computing that are getting a lot of attention and a lot of investment. But the challenge there is, of course, it can be hard to predict when they're actually going to be something you can feel, right? So if you think about quantum computing, I have a couple different snapshots in here. The one on the left is really from science, and it talks about the different types of quantum computers that people have developed so far, and then gives you an idea of even if it's been manufactured or tested today, right? And this was 2016, so there have been some improvements since then, but this gives you a nice idea. Then if you look at this National Academies report on the right side, it's really just illustrated the milestones that we have to get to just to build some kind of quantum device that has a practical use, right? And they estimate that something like RSA encryption is not really under threat until in the next 10 years. So that's the National Academy. So just to drop back and think about this a little bit more historically, So here's a fun question. When was the first field effect transistor patented? So we all know about Shockley and Kirby and some of the others out there. When do you think somebody actually got a patent on the field effect transistor? Does anybody want to shout out?
Early 1900s.
Which one?
Early 1900s.
Yeah, well, there you go. See, you're a hardware guy, aren't you? So, right. So, it is the 1926, right? So, you can go in on Google Patents and look it up. It's there. And so, think about that. Somebody patented the idea, just the theoretical idea for a field effect transistor in 1926, and the patent had expired by the time Shockley had basically done the work in the late 40s, right? And so there's a long time frame there. Now, investments differ, and there are other factors there, but I thought that was interesting to think about. Now, the last one's where I just want to spend a few more minutes, this architectural specialization. This is where we are. This is using CMOS more effectively for very specific workloads. And we've been seeing this with GPUs and SoCs and many other things. If you go to a conference like Hot Chips, you see it. If you listen to Amazon and Facebook and many other companies, they're building their own chips because it's cost effective. Apple, you guys have one of these in your pocket that have maybe 40 different types of IP on one core that do everything from encoding to encryption to GPUs to many other things, right? And so it's happening. And of course, we've used FPGAs that have their benefits and sometimes downsides. And also, the Xavier SoC I mentioned earlier. It's really interesting just to drop back and look at the diagram of this. It has an 8 CPU core cluster with ARM cores in it. It's got Volta GPU cores. It has a deep learning accelerator. It has a vision accelerator, and then maybe 3 or 4 other types of accelerators on it. So just to be clear, I think in the next 10 years, this is very much like what our next generation systems are going to be like. And then, of course, there's mobile phones and Snapdragon. Snapdragon looks very much like the SoC that I mentioned. So, and if you don't believe that, DARPA has been investing heavily in things like RISC-V. So you can create your own chip. And if you go to a DARPA conference these days and listen to some of the program managers and positions they're taking, they want to make chip design so easy that basically you can pull out the IP as well as an open tool chain to allow you to build and verify chips before you send them off to the foundry. And this is the PM slide you see here. The bottom, that's a picture of him sitting on the beach building an SoC and sending it to an online service that creates the board and basically mails it to him like an Amazon package, right? Now, think about the consequences for that. Think about every chip being different, right? That's something that really is difficult to think about from a software perspective. So just to summarize on the disruptions, on this chart I have here on the right, some of the disruptions may not even be something that we see or are exposed to the apps. What you see in the cells here, the color and the number, give you a feel for how disruptive they'll be. For example, if a carbon nanotube transistor is developed, it may just be completely hidden from us. Meanwhile, something like quantum computing, you have to rewrite your entire algorithm and rethink the entire problem that you're working on, just because it is fundamentally a different computing paradigm. Now, if we look at DOE, this has certainly impacted us. If you look at timing, of course, we've had heterogeneous cores for 8 years now, and Frontier will continue that. We've got the deep memory hierarchies with non-volatile memory, and we have really plateauing I/O performance. And that is something that a lot of people don't recognize, but really need to think about. The I/O performance on Summit today is about 2x what it was on Jaguar 10 years ago. right? But the systems are massively different in terms of memory and compute. And then if you look at Frontier, this is a system that's been announced but really hasn't been fielded yet. It's our Exascale system. It's going to be an AMD platform. Right now, our projected peak performance will be greater than 1.5 exaflops. And it will be combining AMD's processors and GPUs. And so that is going to be a new type of system architecture for us. And then I added this just to give you an idea of what some of those comparisons were. Right now, Frontier is estimated to be about 29 megawatts, and there are plenty of infrastructure improvements underway now at Oak Ridge to add new power stations and cooling towers to address that. So just to summarize, so that's a lot of complexity, and so that's what I meant earlier when I said complexity is our biggest challenge. If I go to all my 25 users in ECP and give them this large palette of architectures that they have to worry about, they really need solutions that can help them with that. And that is because the programming models are very complex. You have to manage MPI or use some other paradigm like Legion or HPX to manage the distributed memory part of the execution. Then on the node, you've got OpenMP, and you have things like pthreads you can use there, or maybe even some user-level threads. And then to manage the accelerator, you have, as we talked about, OpenACC, CUDA, OpenCL. That's a lot to get right. That's a lot to ask of our users, right? That's very fragile. The tools don't work well with these software stacks. It's very, challenging to just keep all of that balanced on a top of a pin. So, complexity is it. The two main implications of that are the design. First, how do we design the systems so that they work the way we want them to? Even things like simulating these systems is difficult because they're so complex. Programmability is the one I'm going to focus on today, and it basically tries to answer the question, how do we design applications with some level of performance portability? I mean, this is a major challenge right now. There are some tools and compilers that do not run across the systems we have today, and it's a big challenge. So let's take a moment and dive down into programming systems. And this is where there's a lot of activity going on, a lot of activity here that I know at different locations. And so this is what I got when I asked the question of how do all these programming models fit together, right? If you look at this, it's a tangled nest of dependencies and interactions that is very, very challenging to both explain and to maintain. You have things like, low-level models like I mentioned earlier, HIP, CUDA, OpenCL, then you have the directives, and then you have the meta-programming models, and they all have their own strengths and weaknesses. But this really isn't the story we want to be telling users right now, right? And so part of the work we're doing in our group to look into this is using directives with a research compiler we have called OpenACC. So why do we choose directives? Well, we selected directives because it really is an easy way to get the solution into the existing codes. Now, it's not perfect, but it's a lot easier than asking the users to go back and write their code in a new DSL or rewrite their code in C++ so that they can use some of these new capabilities with metaprogramming. And so if you look at this, what you see is the OpenACC schematics on the right-hand side. Basically, we can ingest things like OpenACC and some features of OpenMP. Then we parse that. The important point here is we keep it in a high-level intermediate representation. So for those of you familiar with the different compilers, LLVM has an intermediate representation, but it's generally a low level. And so it's hard to get things like deeply nested loops or complex data structures extracted from that low level and then analyzed. You have to really recover it. What this high level IR allows us to do is really keep a lot of that information at a very high level so that we can do those transformations with the original information. It also lets us make things like data transfers and kernel launches and all of those activities first-class citizens. So they're just part of the intermediate representation and they can be analyzed and optimized. And then we have basically a back-end where we map it to the different target architecture's native driver and native language. And so what you see on the far right is that runtime, and it's really just a way to normalize what the different calls are for data transfers and launches and so on. And then we generate that code and hook it up with the runtime and run the application. So I wanted to take a minute and talk about FPGAs. The GPUs are something a lot of people have seen before. The FPGAs are still very popular, and a lot of people are experimenting with them now as a potential solution. What we wanted to do was see how far we could get by taking OpenACC and trying to map it to an FPGA. And so the benefit in that is there are specific optimizations for the FPGA that we can derive from the fragments and from the code itself. We might be able to automatically generate optimizations for things like shift registers and data alignment problems. And so that's what we did. If you're not familiar with how this works, we target the OpenCL that's provided by Altera in the case I'm talking about here. And so you're not dealing in LUTs or very low-level concepts. You're writing OpenCL, but that OpenCL is optimized for this specific architecture. And if you look at this architecture here, and provided by Altera, this is how you have to think about using that FPGA. You have a kernel pipeline, and it can have a depth, and that's configurable because you are running on an FPGA. You have a vector width, and you can also change that. And then you can just replicate these compute units. So if you decide to balance these out with a longer pipeline depth and reduce compute units, really it's all up to you. And if you programmed FPGAs before, you know that's part of the game. And so we did it. We have it working. It generates code, and then we wanted to start looking at optimizations for that. And so one of the optimizations that we found was if you just think about OpenCL, traditionally you have to transfer the data back at the end of a kernel execution, and you transfer it back to global memory. And then if you have another kernel execution after that, you may have to transfer the data directly back into the device that it just came from. Now, Altera provides some channel. This is a concept they created originally as a proprietary extension to allow you to pass the data directly from one kernel to the next kernel in the FPGA. So it never leaves the logic of the FPGA. It continues to execute there. And it provides a tremendous performance benefit. Now, the way we did this was take OpenACC and add a fragment to it. Now, the code you see here is what gets generated when you execute the OpenACC compiler and then you generate some code. The bottom shows you what the OpenCL code with channels looks like. And this, again, is the Altera extension. You basically write that data into what's called a pipe, and then you read it from that. Now, when you're looking at the transformation itself, the code again is up the top, and you can see that what we do is we add this pipe in and pipe out right here, down at the bottom, and that's a new extension to OpenACC. Something that we couldn't derive automatically, but it's something that we could introduce and evaluate, and so that's what we did. And we found that it worked well. There are some conditions that it doesn't work under, but if you know that when you're writing the code, you can accommodate that and try and structure your loop so that it's easy to match that constraint. So that was the pipe optimization. We have a bunch of other optimizations that we've worked on, and some of those target things like reductions, so mapping them into shift registers, or sliding window for things like convolutions and other items. But we're optimistic right now that you can use a high-level programming model that's reasonably portable and even target things like FPGAs. And so that's the point of this exercise. We have a lot of details in the paper that I don't have time to go into today, but this gives you some idea of what the performance was like. And so what you see here is the black line in this graph is normalized to sequential CPU execution. Black is the FPGA. And what you see here is in some cases the FPGA is competitive with some of the other devices we have, like the NVIDIA GPU or the Xeon Phi. And in some cases it's miserable, like in the sparse matrix multiply. But in things like FFTs that you can pipeline really well, it does surprisingly well. So moving on, the next thing that we started looking at was runtime systems. So again, there's the possibility that almost every system we run on will be different. And what I mean by that is, even if you look at two systems like Summit and Sierra at Oak Ridge and Lawrence Livermore, they're pretty much the same, except they've got different configurations for memory and different configurations in the terms of the ratio of GPUs to CPUs. Some users actually write their code to that and know exactly how many GPUs are on the system and do a lot of advanced optimizations based on that. I think that's not a good thing to do. And so what we need to do is find a way to abstract that away from the architecture and provide an API to the user so that they can write it once and run it anywhere. And so over the past year, what we've been doing is trying to build a system to do that. The system is called Iris, and Iris is meant to map kernels to the heterogeneous architectures and the native programming power that they're using. Now, why is that important? Why should we even worry about programming models? If OpenCL works everywhere, right? Well, we found out OpenCL is not available everywhere. It's not available on something like the NVIDIA Xavier platform. So we had to download Popple and try to get it to work there. If you look at OpenCL, there's not really a good way to use it on an ARM core, just to run on ARM multi-core. And so what we wanted to do was raise that level of abstraction, so not only did you target a specific architecture, but you could target a very specific programming model. And that's what this diagram illustrates. So far, we've been able to generate code for these different programming models you see here: CUDA, OpenMP, Intel, OpenCL, and then OpenCL in general, and then HIP. It's been the recent addition that we've added, and we added HIP because of Frontier. And then what Iris does is take that and information about where the preferred execution for the kernel is, and then runs it on the target device. And so the important thing to note here is you can have all these kernels running in one program, right? So if you have an SoC like we were talking about earlier, that has some ARM cores and some GPU and maybe an inference engine in it, Iris can actually manage all of those together. Let me show you a little bit more about what it looks like. So in the graphic on the right there, you see the kind of the hierarchical decomposition of Iris. We have an Iris compiler, which is really OpenARC right now. Iris doesn't do code generation. It can do compilation because things like OpenCL support compilation. But then those tasks get handed off to the Iris runtime system. And then the runtime system knows how to interact with OpenMP and CUDA and HIP, and then OpenCL, multiple OpenCL devices in a shared node. And then you basically create tasks. Those tasks can have dependencies between them. They can be explicit tasks, or they can be tasks that are hazards or basically data dependencies between those tasks. A little bit more about the architecture. What we're assuming here is that you have something like a DAG-style task parallel execution. And so DAGs are really popular in computing. And so, so as long as you can start putting together a DAG, it's pretty easy to express and execute here. Now the thing I'll mention about this is there have been a lot of runtime systems, a lot of task-based runtime systems, right? And we looked at a lot of them, and we probably had 40 of them in the list that we looked at. What our goal here was to write a tasking system for very heterogeneous systems. And we really didn't find anything that would run across all the different types of devices with their native programming models that would support this type of execution. Right now, we've got Iris. It's running on several architectures, and these are some of the architectures we have in our shop right now. We have Oswald, which has a P100 GPU and a Stratix 10 in it, along with the Xeon. Then we have a Summit node, obviously, that has several V100s and Power 9s. We have AMD, and then we have the two SoCs, Xavier, that has the ARM cores and the Volta cores, and then Snapdragon, that is also ARM and their own GPU. And so there's a picture of it booting and running on all of those. I know it's kind of hard to see at this resolution, but the important point is when it boots up and starts running, it discovers what's available in the system and then makes that available as a device to the application. We haven't quite got to the point where we can generate and store all of the different programming models that can run on those devices ahead of time, but that's something that we're working toward. And this includes Snapdragon. So one of these is running on Android cell phone, right? One of them is running on a Summit node. So at the end of the day, what we want to be able to do is have this runtime run from a cell phone to a supercomputer, and that's what we're targeting. Some of the task scheduling, and this is where some of the fun, interesting work comes in. You can see here that really Iris right now is providing many mechanisms, and this includes scheduling tasks and running them, managing the devices. But we really need to figure out what the right device selection policies are. And those policies could come from many of the ones that we already know about. The user could specify it, we could profile it on different devices and then store that information. We're thinking about performance modeling using some of our Aspen performance modeling tools. And then there's other ways to do it, where you look at some characteristics of the kernel before you execute it. And then a task scheduler dispatches it on the device that's of interest. And it can do load balancing too. And so the neat thing about this is if one device is swamped and another one's completely empty, it can do some quick analysis to decide if it wants to make use of that empty device. And then this is just an example of the Saxby example in Xavier and the kind of the details of how you run that. And I'll show you some code in a moment. And this is running, again, CUDA and OpenMP. So it's running OpenMP for ARM and CUDA for the NVIDIA GPUs. This is the Python code that's actually running there. And so we have C++ and the Python interface to this. And this gives you an idea of what the Python looks like, as well as the CUDA kernel. Remember, Iris doesn't do code generation, but there are certainly many many tools out there that will do that for you. And here's the one that's saying with the OpenMP code, and you can see on the right what the OpenMP code looks like, and that gets loaded and run on the ARM cores. So lastly, just looking at the memory consistency management, one of the things I mentioned was this dependencies. And so if you know OpenMP task dependencies and some of the other ways that you can represent dependencies, what you see here is really a representation of that. So if you look at this, what you do is you start creating your kernels, and then you identify the data that you need to have to run those kernels. and then you can submit the kernel to run on a given device. At that point, Iris knows where the data's got to be executed. And so it can actually inject data transfers from one device to another because it knows that pending dependency is about to be realized. And so when it finishes computing, it can actually do that automatically. And in this example, there's even an option in the submission to say, I just want the kernel to execute wherever the data is. So if it's already living in the GPU, don't bother offloading it to another device. Just keep it there and run it. And so there's a lot of interesting things we can do with that. So just to bring it back and close up, so Future Tech, we've got this vision, we've got a lot of different things that are happening in response to the architectures. I hope if you didn't take anything else away from what I was saying, it's really becoming a burden for users to tackle these complex architectures. And I've given you an idea of what we're doing with OpenACC and Iris. I know there's a lot of other work going on out there, but I think we really risk not getting computational science or basically anything else done besides porting to these different architectures if we keep on the trajectory we're on. So just to recap, I'll leave this up here. We have some work that I did not get to talk about. I'd be happy to chat with you about that later. OpenACC and Iris are both open source. We haven't made a public release yet, but we're happy to share it with people if you're interested in taking a look at it and starting experimenting with it today. They both live on GitHub. Okay? Thank you very much.